Simple topic of conversation for my session this morning. It's all about device offsets. And the big question is, should device offsets go to the big red guillotine and die? That's my question this morning. Do device offsets have a place in modern day wireless design and survey? And if they do, what is their place? Okay, that's what I want to talk to you about. But before we start talking about device offsets, I want to talk back a little bit and just think about how does a device receive signals and measure signals. Now, we all probably know that an access point will transmit something at a signal at some sort of power level. On the slide here, I'm showing it at 10 dBm, and that signal will travel through the air and be received by a mobile device. And that mobile device will probably report that it's receiving the signal at some level. Again, on the slide, I'm showing mine at 68 dBm, but it's going to receive it at some level. So how can we calculate the loss of the signal from the AP to the client? Well, we have a very well-known algorithm for doing that. It's called free space path loss. Free space path loss is a really well-known algorithm. It's based upon something which we call the inverse square loss. And what that algorithm says is that if we take a measurement of a signal at some distance from the AP, if we're looking in the chart on the screen, let's say we take it at 1 meter. Whatever we measure the signal at 1 meter from the AP, if we go to twice that distance, we will lose 6 dB. The signal will be a quarter of what it was when we first measured it. So every time you double the distance, you lose a quarter of the signal. You'll get a 6 dB loss. That is something which we always measure with free space path loss. Something else that's quite interesting with this algorithm of every time we double a distance, we lose the bandwidth is you realize how quickly an RF signal loses power. Let me give a little simple example. My little clicker here, let's pretend it was an antenna. If I was to measure the signal coming from this antenna at 1 centimeter from the antenna, and then I went to 2 centimeters, it would be a quarter of the power it was at 1 centimeter. If I went to 4 centimeters, it would be a 16th of the power it was at 1 centimeter. Believe it or not, the same thing would happen if I said millimeters. What that means is when the signal first leaves an antenna, it drops off very, very, very quickly. And you see that drop off in the curve on the graph here. We lose most of our transmit power over the first meter. And then from that first meter, every time we double the distance, we lose 6 dB of the power. Many of you in this room will have known that. And because of this well-known algorithm, we can predict what signal strength we're going to get at different places from an AP. It's how wireless design tools work. We put an AP on a map and it shows us what the signal strength is as it passes around. But here's the thing. That signal strength, if we're measuring free space path loss, is before any device has received it. When a device receives a signal, it has an antenna, for one, and antennas often have a receive gain of some amount. Okay? They sometimes have what we call a negative receive gain. We're going to talk a bit more about that as we go for this presentation. And they have some receive circuitry. And then once we've received the signal and it's gone through my antenna, gone through my received circuitry, I am then going to measure using some method, which we're going to talk about, the signal strength I receive. And we call that measurement RSSI, Receiver Signal Strength Indicator. And then I can pop up, and maybe if your device can display the signal strength, it's going to tell you what it's received. That will not be the same as the free space petaflops. It could be more, it could be less. But there will be a different value. So how does a device measure RSSI? Well, if we look at the 802.11 standard, and I've got a little snippet on the slide here, it says that RSSI is a parameter in the range of 0 to 255. That's what it is. It's a value in the range of 0 to 255. So it's an integer, okay? And it's to be measured by the physical layer observed at the antenna connector, and it's going to be measured when it receives the physical layer preamble. So whenever you see a signal strength reported by a device, it is the signal strength it measured when receiving the preamble. Now, why is that important to understand? Well, first of all, what is data rate do physical layer preambles go at? Anyone know the answer? Keith is saying 6 meg. That is exactly right. They go at, if it's an OFDM data rate, so not 802.11b, but anything above that, is going to go at 6 megabits per second. So our lowest possible data rate, that is 6 meg, is achieved on a 20 meg channel with BPSK modulation. So whenever we measure a signal strength, we're measuring a single spatial stream on a 20 meg channel, regardless if our data is going at 2 spatial streams. Okay? That's what we measure. The other thing to say about RSSI is RSSI was never designed to be a really, really accurate signal measurement. As we can see from the signal, it says it should be used in a relative measure. Relative to what? It's going to be used in some sort of relative measure. So let me talk about what it's relative to and how we measure it. So RSSI is going to come up with a value between 0 and 255, but it doesn't have to use all those numbers. Some vendors measure signal strength between 0 and 60, some between 0 and 100, some do 0 to 255. Okay, so what they do, different chipsets will split the signal they can receive into bins, if you think of it. You can think of it as bins, and they can measure particular signal strengths between 2 values, depending on what they see as their max RSSI value. One vendor might have 100, that's vendor A on my diagram, one might have 60, one might have 30, but they're going to measure signal strength in these different bins. Obviously, if I only measure 30 bins, there's only 30 different signal strengths I can report, maximum. Then what these chipsets do is they will then convert this number. So let's say my RSSI is 10. They'll convert that to a dBm value. That is where you get to it's in a relative manner. They have a mapping from its RSSI value to a dBm value. So let's have a look at what some examples might be. So vendor A might go from -10. At the highest it can measure, all the way down to -113. And then it's got 100 values between those points. Vendor B might be -95, might be the lowest signal strength it can read, and the highest might be -35. That means you'll never, ever get a reading stronger than -35 from vendor B. It just can't give it. If you're receiving a signal strength stronger than that, it'll still report it at -35. Vendor C might be minus 100 to minus 50. You'll never get a signal reading higher than minus 50 from that vendor. So this is the way our clients read signal strengths. Okay? So it's interesting. Now, years gone by, sometimes chipsets and vendors would publish this type of information. And actually some of these numbers on this slide come from a number of years ago where I actually could tell you which vendors these are. I'm not going to, but I could do because they used to make this information available. Nowadays, good luck if you can find it. No one tells you. Okay? This is kept secret. So what do we do about that? Well, I thought in preparation for this talk, why don't I see if I take my new iPhone 15, I wonder what's the strongest signal strength I can possibly ever read with it and what's the lowest. Now, this is just what I got on my test. Someone from Apple today, they might go, oh, actually, no, we go higher. Maybe they do. But from putting my iPhone on an AP, so I was literally touching the AP, and I tried it a few different ways, touching it, to walking away until I couldn't see the signal anymore. And I got from an iPhone, the maximum RSSI I could get was minus 21 dBm, and the lowest was minus 96 dBm. So I suspect it's somewhere, that their min and max is somewhere around those values from my testing. Just to give you an idea. But because every device measures it differently, okay, and they have this mapping, every single device has different receiver circuitry. Every device is going to receive signals differently. So again, I did another little test. I took an iPhone, an iPad, a MacBook, and a Dell laptop. The Dell laptop had an Intel chipset in it. And I taped an area on a desk, which was at a set distance from an AP, and I put each device in the same area, static still, and then I took an RSSI reading from each device. Now, I will be honest, this isn't an average RSSI. I didn't sit there and do this really scientifically and take 100 readings and take the average. I just took one as an example. Okay? But it's interesting, isn't it? I took a 2.4 and a 5 gig reading from the same AP. I'd set the transmit power of both 2.4 and 5 gig to be the same. You're going to ask me what I set it to. I can't remember. But it doesn't really matter for this point of view because it also depends what distance you're at, doesn't it? But the 2.4 and the 5 gig were set the same. I think I've maybe set them both to 10 dBm. Okay, I think. But it's interesting because we look on the iPhone, it could hit 2.4 minus 77 dBm, 5 gig minus 88. That's a 10 dB difference just between the two bands. We look on the iPad, and we can see a similar sort of difference there, minus 73 to minus 86. But not only is there a difference between 2.4 and 5 gig, there's a big difference between devices. The MacBook easily wins out on 2.4 as seeing the signal the strongest. But actually, when we look on the 5 gig band, it was actually the Dell laptop that had the signal the strongest. But we look at the variation, there's actually a really big variation between devices, especially on the 2.4 gig band, everything from minus 68 dBm to minus 77. Same place, same location, just different devices, different frequency bands. So why is that? Why do we get so much variation? Why is it when I compare my phone to my laptop, sometimes I might see a 10 dB difference in signal strength in the same place?
Maybe receive sensitivity because of the chips, that kind of front-end equipment they use.
Is it receive sensitivity? Well, in one sense, you're right, but let's take a bit of a look at the antennas in these devices. Now, when we think of an antenna before we look at it, what do antenna, we often talk about antenna gain, don't we? And if we've got a 10 dBi gain antenna, we'll get 10 dBi gain receive on it. So we generally think of antennas as giving us gain, okay? And if we look inside a laptop, you can see that laptops often actually have omni antennas built in, physical antennas up the side of the screen. And they're going to often give us a nice, strong gain to the signal. My Dell laptop will have been similar to this. It'll have had these laptops up the antennas up the side of the screen. When we look inside a phone, these are the sort of antennas we see. One of these is an Android antenna, one's an iPhone antenna, but the antenna's been bent to fit into the phone casing. You know, we don't tend to have now phones with antenna. My first mobile phone, it had a little pull-out antenna on it. And I thought it looked really cool.
I heard that in mobile phones is negative gain, I believe.
We'll get there. So, a little pull-up one.
It wasn't ever connected.
It wasn't ever connected.
Purely there for aesthetics.
The Motorola one, yeah, mine wasn't actually. It was prior to even that phone. But it was great. It had a little pull-up phone antenna, and I thought it made me look really cool. But they then went, actually, that doesn't look really cool. It's much better if you don't see the antenna and you don't have a big antenna sticking out of your pocket, okay? Because that can be misinterpreted sometimes. So when... I'm glad some people got that joke. Okay, so what they do is they build the antenna into the phone itself. But then to get it to fit, it ends up being bent. And when you bend an antenna, instead of getting a positive gain, you get a negative gain. So actually, whatever the signal strength is, we're going to receive it less. And we're going to receive it as a lower signal strength. So depending on the RF circuitry is really going to affect how a device reads a signal. Not only are we using an inaccurate signal measurement, RSSI, and we've got, based upon what bin and everything our chipset does, we've always got to think about the antenna and receive circuitry. And those two things combined are going to lead to very different signal readings. But you see, it's not even, that's not the only things we need to contend with. You see, have you ever looked at a single device over time in the same place? Do you get the same signal strength all the time? No, you don't. We have things like multipath to contend with, don't we? And multipath is an issue when we're talking about single spatial streams, which the way devices all measure signal strength is on a single spatial stream, because it measures it on the preamble, as we've already discussed. So when you look at a RSSI reading off a device, and this is a device I did, again, it was actually on the same location, it was in one location on a desk, not moving, just taking signal readings over time, and I graphed it. The highest I saw was minus 45 dBm, and the lowest was minus 63 dBm. That's a big difference, isn't it? Now, they were the outliers. And obviously the average was much closer, you can see from the graph, much closer in the middle, but there was a lot of variation. That was with its static. What happened? Well, I'll take my device and I'll try turning it, or flipping it, or turning round with it. Now I'm also on this location. I'm not moving from a spot. And if we think about doing a wireless survey, we want to know what's the signal strength here, don't we? And we're going to get one reading and say, that is what we get here, minus 67 dBm there. But what happens when I'm studying that device? What happens if I'm using my phone this way or I'm using it this way? What happens if I'm facing the AP or I've got my back to the access point? What's the difference? So I took the same device and I literally did this. And I turned around, I raised it up, I made it lower, and I moved with the device as much as I could. And this is what that graph looks like. I managed to get a maximum RSSI of minus 38 dBm with a minimum of minus 75 dBm. You know, it's huge, isn't it? You're talking 30 plus dBm variation. That is a massive deviation in signal strength in the same location. If I compare it to the static, you can really see the difference. The blue line's the static, the orange is the variation in signal strength. But all of these were taken in the same place. And just to maybe hurt with your head a little bit more, okay? This is showing the signal strength received by on one packet inside OmniPeak. And you can see that the number of spatial streams is 2. So it's a 2 spatial stream frame, okay? And the signal strengths that came back from the driver it actually passed up 4 signal strengths. A little bit odd. Why does it pass up 4 signal strengths? A minus 62, a minus 65, a minus 59, and a minus 92. That's a bit odd, isn't it? Why would it do that? Well, let me go back to thinking about I'm transmitting 2. If I'm sending 2 spatial streams, I'm going to send one from one antenna, one from another. Yeah? A receiver, let's say they've got 2 antennas. What do we receive on the first antenna? They receive both signals, don't they? A combination of both. On the second antenna, I'm going to receive a combination of both antennas. So effectively, I've received 2 signals on one antenna, 2 on the other. That's 4 signals. Yeah? And then I compare the combination, and so I pull out these separate signals, and therefore it can give me 4 different signal readings, potentially. Well, that's exactly what these drivers do. They then give an overall signal level, some sort of magic in the driver to come out with a signal reading. But the rail signal, and look at them, one of them was minus 92. Now, I'm sure we probably didn't use that because that was one that wasn't very good, and the others are more close to each other, minus 62 to minus 59, but there's still some variation. So, I'm telling you all of this to help you realize that RSSI isn't a really accurate signal reading. So let's go back to thinking about a design. When we do a predictive design, we are generally looking at a signal before any device has received it. If we're just plotting free space path lots. The great thing about it is that is something we can consistently model every single time. I can take any device, and if I know the power at one distance from it, I can tell you what it'll be before at another distance. What I can't tell you is how it'll be received by a device. Because of all these variations, there's just too many factors. So I'm a big believer, therefore, in not using any offset for design. Because the minute you go and say, I'm going to offset it to a device, here's my question. Which device? In which orientation? Are you doing it when you're facing the AP, with your back to the AP? Are you going to do it when they're using it in portrait mode, landscape mode, up in the air, where they're looking down at it? Because all those things are going to affect it. And could affect it quite hugely. So that's the issue we've got, okay? So what solutions have we come up with as an industry? Well, before anyone talked about device offsets, so you go back a long time, I think as an industry we came up with a pretty good solution, okay? And that was, we designed to a primary signal threshold. Many of you will know different primary signal thresholds that have been recommended by vendors over the years. Mine at 67 was a really common one. Many of you used, and then more recently people have said, well, actually mine at 65 might be better for modern day networks. But where does that value come from? And why? Because mine at 65 is actually quite a strong signal strength. And as a client, you give me mine at 68, I'll work really happily on that. But where does its mine at 65 come from? And why is it important? Well, when we started thinking about signal strength and what we should design to, everybody knew devices were going to receive signals at different levels. The whole point of mine at 65 was it's strong enough that it's a good average. So yes, some devices will hear it louder, some will hear it lower, but most of my devices will get a good quality signal strength where they can get a good MCS value and they can work. That's why we have a primary signal strength. That's why people came up with this idea. As I say, some devices will actually see a better signal, some will see a worse, but overall it'll work well. And think about it. You know, we've become a little bit obsessed with heat maps, I think. Heat maps are great, I'm not saying that, but we go, oh, there's a bit of grey there. I'm below mine at 65. Must fix that. And we become, a tiny little grey area and we get really worried about it. Do you think our users, the people who use Wi-Fi, care whether I've got mine at 65 here or mine at 68? Do they care? What do they care? Can I connect? And can I access my applications and do what I need to do here? I don't give two monkeys what my signal strength is. Most users don't even know. So actually what we want to do is we want to provide a good coverage for most of our devices. Okay. What have we then done as an industry? People have then gone, oh, devices all receive signal strength differently. So let's offset our designs. Mine at 65 was a strong signal strength, it's going to be good for most devices. But now I'm going to take my least performing device and offset and say that device has to get mine at 65 everywhere. What we often call our least capable device. The problem with that is you've now made the strongest device is going to hear it like what? Minus 40, minus signal strength? Maybe minus 45? That's really loud. And you end up having loads and loads of APs. Have you ever been in buildings that have too many APs? Have you ever designed a network? I won't make you put your hand up where you've put in too many APs and then had to turn some off. And have you done that using a device offset for your design? I see it so often the time. Often when people offset the design, they end up putting in too many APs and they end up getting way too much signal strength because they're trying to fix a problem twice. We've got a primary signal strength at mine at 65, which means that'll do well for all my devices. Now I'm going to offset it to my lowest device, and I'm trying to fix a problem twice. And all it does is you end up designing way too many access points into your design. So here's my rule for design. Never apply an offset to your design. Now, picking a good primary signal strength, that is important. And you may, to work out what's a good primary signal strength, you may do some device signal measurements. And you may go, well, hey, my laptops and my phones have a 12 dB difference. And you may look at some offset measurements to come up with what's a good primary signal strength. I'm not saying you wouldn't do that. So there is a case for measuring devices and looking at the offset between the clients that you have in your environment to say what would be a nice, good primary signal strength that we should design to. But what you don't need to do is then offset that again. So there is my rule for design. Here's my rule for survey. Always offset your survey results. Okay, let's try and go there now. Okay? So don't offset your design, always offset your survey results. You're now going to say, Peter, you're contradicting yourself. Well, I'm not, because we've got to go back to this little diagram that we've looked at a few times. What we design, I'm saying design before any device has received it, a signal. The problem is when we survey, what do we survey with? A device. Some sort of side. We use a sidekick, we use a nomad, we use, and that's our eye device. We use some sort of device to survey with. That is a device which receives signal strengths and generates an RSSI, and has all the same faults and inaccuracies in signal reading as our rail devices do. So when we're surveying, we're not surveying free space path plots. And very often, survey devices have very, very sensitive ears. They're very good receivers. They're designed to be that way. And there's nothing wrong with that, so we can pick up as much data as possible. But it still is a device. And therefore, it's not going to show me, my survey results will not match my design. Yeah? Because if I've designed without any offset, my survey results are not going to match it. So I'm a big believer in when you are validating. Now, there's two types of surveys I want to talk about this morning. Let's get this one out first. There is what I would class as a validation survey. You are validating your design. That is the purpose of your survey. The other type of survey you may do is what I would class as an assessment survey. You are going into a network that exists and you are assessing the network. Does it meet the requirements? You probably didn't even design it. Okay, it's an existing network and you're going in just to assess the coverage. And I think you have to treat them differently. Okay, and we'll talk about why. But when you are validating a design, what do I want to show to the customer? Look, here's a heat map that matches my design. Yes, this is what I designed for, and yes, I meet it. Therefore, I really believe in something I call a device offset. As a design offset. A design offset is where I'm going to try and offset the results of my survey to take it back to that free space path lots design. So how do I go about doing that? Well, I take my survey device and I'm going to go to, generally I go to somewhere like maybe about 5 meters from the AP, and I'm going to measure what signal strength I get. And I will compare that to my predictive design and what it said the free space path lots value should be. And I'm going to measure it at 10 meters. I'm going to measure it at 15 meters. You could take some other readings, but don't just do it in one place. This is the key. The other key to this, if you're going to get it, obviously the survey device has some inaccuracies. The best survey devices are going to be really, really consistent, but how do you wear it? If your body gets in the way, then when you're taking these readings, you want to try and have the survey device in the exact same orientation, in the same position as it's going to be for when you're going to survey. So think about that, whether that's, you're wearing it on your side, you're sticking it on your head, you're strapping it to a big pole and walking with it in the air, whatever you decide is the most accurate measurement. And generally what I would say is do some testing with your survey device as well. Maybe wearing it on your side isn't very good, because actually you walk this way and you're going to measure one set of results, you're going to turn around, now your body's in the way, and you get different set of results. So try it in different places. What you ultimately want from your survey device is, people talk about the most accurate survey device in the world. It depends what you mean by accuracy. What I want is the most consistent survey device. I don't care what signal reading it gives me, I'm going to offset it, but I want it to be consistent. I don't want it to vary by 10 degrees. I don't want it to keep giving me different readings. So what we really want is a consistent survey device. And how you carry it will affect that. So do some testing with your particular device. Work out where's a good place to put it. How should I carry it so that I'm actually getting more consistent readings? And then when you come to coming up with a design offset, however you've decided to carry it, you need to measure this offset in that same orientation. So if that is, as I saw Fanny do once, you've got a hard hat with your survey device on top of it, that's fine. Take your readings, your offsets with your hard hat with your survey device on. That might give you the most consistent results. And if it does, do that. Doesn't matter if you look stupid. Okay? It's okay to look stupid. I know, I do it quite often. Sometimes I stand up in front of a crowd of people and talk about Wi-Fi 10. It's okay to look stupid. So let's get really accurate, consistent results. When you do this, therefore, you can then what you're going to do is compare your measured data to your design data, providing you've... And when I do this test, by the way, I'm doing it in free space. No walls, nothing like that. Okay, in a way, that's really important. Sometimes I even do it outdoors. Very often, I've got an area near my office where it's just big, it's open, and I put an AP up on a tripod and we measured it. Completely free space, so there's nothing in the way. Okay, that's also an important element of this. You want to make sure you've got clear line of sight to the AP. And then you get a design, and then out from these measurements, you're going to average out and look at what is the design offset. They won't all be, the readings won't all be exactly the same offset, but you should get an average. That way, we can take our surveys, we can offset them to our design, and at least what we're showing the customer is consistent. Hey, here's your design. Look, I validated it, and it meets my design. Now, you need to have confidence in your own designs, therefore, that the primary signal strength you've said you're going to design for will work. But that's why we put all the work into gathering requirements and doing measurements of devices and having that confidence that our design will work. I don't like showing customers, oh, this is what it looks like from an iPhone point of view, because it confuses them. What they want to know is, did you meet... You've designed, here's the design you've given me to meet my requirements. Is what you've installed, does it meet it? And I want to see a consistent view. What about the validation? Okay, what about when we're going in and we're doing an assessment? So maybe go into the example is a retail store on the slide here, but you could be going into any sort of survey. And one of the reasons they've asked you to go in is because they've got problems. And they've got problems with these new devices they've just brought. They're not doing very well on the network. So you do your survey, and we maybe have this nice green map on this side. But actually, they're having a particular problem with a particular device. Now that is when I might do a device offset. Because I want to know how that printer, let's say wireless printer, has seen it. This was a wireless printer, which was, on average, it was about 10 dB less than my laptop. It was a very poor device. And they were having some problems in very particular areas, particularly around the aisles where they sold wine and beer. That was this area just here. They were struggling with printing. So what I did was I measured a device offset, and then I looked at the coverage from the point of view of that printer. And in that case, I think that is valid because you're assessing not against the design, you're assessing against, do I have enough coverage for this particular device to work? You may even do that in your validations, but just do it for you. I would never send that to the customer, okay? Because it can confuse them. As I say, maybe the grey is actually okay. Because, yeah, I'm below my primary signal strength, but I expect the printer to be, and actually it'll still work okay. So you're doing it for you as a Wi-Fi engineer to be able to see and assess whether you need to adjust power levels or you might need to put additional access points in. So I think when you're doing an assessment survey, I think that is the only place I would say device offsets really have a place in wireless design. So how do we go about measuring a device offset? Well, in one sense, it's quite similar to doing a design offset, except this time we're going to be comparing our survey device with a real device. So, and again, I would do it at multiple places. Now, where would I do it? When I was talking about design offset, I said go to a nice free open space. I'm a big believer when you're doing device offsets, do it in the place, in the location of the network you are surveying. Because, let's say my AP's 5 meters up on a ceiling in a retail store. I'm going to get different readings if I'm doing it on the floor, and I'm going to take different readings than I would if they were 3 meters. You really do. Maybe I'm in a metal box in a warehouse, and I'm getting I'm going to get, again, different readings than I would get in a carpeted office environment. If I'm in a walk-in freezer in a warehouse, or depending on so what you want to know is how do the device, the customer's device, see signal strengths in their environment, compared to how does your survey tool see signal strengths in their environment, because that's what you're measuring. So I'm a big believer, and I would generally, I would generally get multiple devices if I could as well, because not all devices will look the same. And sometimes, especially when you're taking, if you're in a retail store and you're taking scanners and things like that, sometimes you get some which are just a bit dodgy, they've been there for a long time, and they're giving really duff readings. So I would generally, if I'm using customer devices, I try and get 2 or 3 of them, and I take them around with me, taking these offsets. How do I get a device to tell me it's RSSI? That is a really good question, because not all devices do so. Most devices, you can get it from somehow. So, depending on what the device is. Obviously, Android devices, you can not often install an app or something on it. They'll tell you what it is. There's ways of getting it from Apple devices. It's easier now with the latest firmware. But prior to that, there was a tool called Airport Utility, which would tell you it on an iPhone. When you're talking about mobile devices, so we're talking about manufacturing, warehousing, you're talking about things like Zebra scanners and stuff like that, they often can tell you it, but sometimes you have to go into an admin mode to get it. So sometimes it's about working with your customer and saying, how can I get into, the wireless tool set or the admin mode, and you can normally get it. Sometimes you even need to turn on some device login to get it. So it can be a bit of effort. But the more you work with particular customers and get to know their tools, you start to learn how to get that data. But very often, what I found with a lot of scanners, mobile computers, they come quite locked down for the users. So if you just say to use the device, you can get out of the bespoke app to get to the tool where you can get the signal strength. So you actually have to get it so it's someone's logged into it, like an admin's logged in, where you can actually get to that signal strength. So it can be difficult. But yeah, it's generally a case of even sometimes talking to the device manufacturer But there's normally some way of getting it, even if it's not obvious when you first pick up a device. For So someone was just talking about trying to read it from chipsets. You can often read outside from chipsets. And sometimes if you've got a headless device, a device that doesn't have any screen or any monitor on it, sometimes you can often turn on login. So these wireless printers, actually they could show signal strength at a little screen, the ones I was using last, but sometimes they don't. And you can turn on a log and you can get it from the device log. So that can be a way of getting it. But sometimes you've got to work harder to get signal strength from some devices than other. It can be challenging though. It can be challenging. So I do appreciate that. I'm not saying it's an easy solution. But they are basically my rules. So in summary, no offset for design. A design offset for validation. Offset your validations to match your design, and when you're doing an assessment, that's a place, I think, for device offset. Thank you very much.